All right, you guys, so here I am on the very last page of your Chapter 11 packet. We are going to try and see if there's an association between people who have a very high anger level and CHD, which is coronary heart disease. So if you're an overall angry person, some of you might consider me one of those people, JK, are they more likely to end up with coronary heart disease or have other heart problems? So we've got this table of a bunch of data here, whether or not the person has anger, low anger, moderate, or high, and whether or not they developed coronary heart disease or not. Heart disease. So what we're going to do is we are going to lay out this different type of chi-squared test, similar way to the way we do the goodness of fit test, except this isn't like a one category like colors of Skittles or M&Ms or the months that we did earlier. This is actually two different categories, anger level and heart disease, yes or no. And so that's a different type of test. What we've done so far is chi-squared tests for homogeneity, and that's when you have two different populations. But look at this problem. We have people with normal blood pressure. One single population. That is your clue. That, along with the fact that this is giving us a hint in the question, we have, is there evidence of an association? That means we are doing a chi-squared test for association / independence. Those two are kind of interchangeable there when you define what kind of test you're doing. So I'm going to start by defining the population, setting up my ho and my ha. So here's the starting definitions, I guess. I made a couple notes up here, so keep in mind we only have one single population here versus the two populations for the other two free response problems that we've done in this packet. When there's one population, that's your clue that you're doing an association independence test, not a homogeneity test. There's a lot of like tricky questions, multiple choice wise, and obviously when you're doing a free response question, you need to be very careful in what kind of a chi-squared test you're doing. Goodness of fit is when you're testing a distribution of a single category, like the problems we did in 11.1. And then this section is when you have we've got kind of a two-way table going here. And when you're doing one single population, it's association independence. We also have a clue here in the way that the question is worded. But if you have two populations, that's your test for homogeneity. Okay, so our population here is people with normal blood pressure. We do not have two populations, so that's why we only have one single one here, people with normal blood pressure. And then the ho and the ha. The ho is always no association. And so that's kind of like, we use 0 sometimes when there's a ho, like in problems earlier that we've done. There's no difference or a certain proportion or mean or something like that we're doing. We're assuming 0 is true and we're trying to prove otherwise. And so that's kind of how I remember the ho in this case. There is no association versus the ha, there is an association. So that's the difference between the ho and the ha for these types of problems. I'm going to write out what kind of a test we're doing, and then I'm going to go through my 3 checks that I have to go through: random, independent, and remember, it's not normal for a chi-squared. That would be very, very wrong because chi-squared distributions are not normal shaped. But in place of the normal check, we do a large sample size check. So I'm going to write some of that stuff out now. Okay, sorry, looks like I got a lot going on here. What I've written first is what kind of a test we're doing and why. We are testing a claim about an association, that's kind of word for word from the way the question was worded, between two variables. So my two variables are anger level and coronary heart disease. In a single population. Remember, our population was defined earlier as people with normal blood pressure. We're going to use a chi-squared test for association / independence. And then my 3 checks that I need to go through, similar as the whole chapter: random, independent, and not normal but large sample size. Random and independent are the same as we've been doing this whole time. Large sample size a little bit different. I have a matrix here. I'll explain that in a second. But random, make sure you don't just say random check. Say what kind of a random what we have. It's a random sample, specific number. We took a sample from people with normal blood pressure. Independence, 2 things to check for. Individual observations are independent from each other, so one person's anger level or heart disease doesn't impact or have any effect on somebody else's. And then we did take a sample. We have a random sample, so we need to check the 10% condition. The large sample size here, here is the matrix. All expected counts are greater than or equal to 5. And then you do need to have this note, which is kind of annoying to write, but you need to again explain how the calculator is giving you these values. You need to make sure that you write out how one of those numbers has been calculated. So remember, it's row total times column total divided by table total for each of those 6 locations in the matrix. And that's how we get our 69.7 to go right here. So remember, there is a way to do this in the calculator. You kind of have to fumble around, but you do have to put the initial data table into a matrix in your calculator, which is not part of the stats editor. It's in the matrix part of the calculator. So once you have that table from the original problem in the calculator, and you run the chi-squared two-way test, because we have a two-way table here, it's going to ask you where do you want to store your expected counts, and it's asking you where you put your data. So remember, you tell it that you put your observed matrix in or observed data in matrix A probably. And then it'll ask you, where do you want me to store the expected counts, which is this, and just tell it to store that to matrix B, something easy to remember, so that then you can open up matrix B and see all of these numbers. It's not that hard to do the math and calculate them actually individually yourself if you're more comfortable with that, but there is a way to do that in the calculator also. Ask me in class if that didn't make any sense. So remember, before we're ready to start writing out some actual math, don't forget to define what the alpha or significance level is. We were not given one for this problem, so we will assume 0.05. Remember how to do the DF when you have two different, or a two-way table. It's number of rows minus 1 times number of columns minus 1. We have 2 rows, 3 columns, and so 2 minus 1 times 3 minus 1, that gives us a DF of 2. Now I'm finally ready to start using my summation formula and actually crunch some numbers. So I'm going to write out what needs to be shown for full credit there, and then we'll go to the calculator. Okay, so here's what some of that work looks like. Remember, I'm starting with calculating the actual chi-squared. That's the sum of all of this stuff. Remember, it's observed minus expected. So remember, what I'm doing here is I'm just comparing spots in each matrix. So top left spot gets compared to this top left spot. So that's where those numbers came from. These are all my observed values. These are my expected values. That's why I labeled it expected counts here. So I'm doing 53 minus 69.7 divided by 69.7. And then remember, you only need to show the first 2 iterations of the formula. You can put the 3 dots and then show the last one. That's considered full credit. And that gives me a value of 16.077. And I kind of already talked about how to get that number in the calculator also. Remember, it'll give you the chi-squared and the p-value at once you run the chi-squared two-way test. Remember, this is a two-way because we have a two-way table. Very different from the goodness of fit test that we did in section 11.1, but it'll ask you what matrix you entered your data into, and then it'll also ask for the degrees of freedom, which is 2, and then it's going to spit out this number and the p-value, but I'm going to write out how to do the p-value also in just a second. So here's that p-value. Remember, you're finding the probability or the proportion of the chi-squared being greater than or equal to 16.077. This is our chi-squared value, not our p-value. The p-value represents the area under the curve. Remember, if we were to draw the chi-squared graph, which looks something like this, and we put a line at 16.077 and we shade this way, the p-value is the area here. So you don't need to draw that, but just remember the difference between the chi-squared value, that's your x-axis number that goes here, and then the p-value represents the area. So we have a very, very small area here. And I want to ask you, is that p-value too low? When the p is too low, the whole must go. Remember, we're comparing to an alpha of 0.05, so this is way small. That means we reject our null in favor of the alternate. I'm going to write those out now. So here's what should be written out for your conclusion for this problem. We can restate what the p-value is. It is less than the alpha. Make sure you put both those numbers in there. That means we reject the null in favor of the alternate. Remember, never say you accept anything. We're either rejecting or failing to reject. And since we are favoring the alternate, I'm going to restate what the alternate was. There is an association between, and here's your context, anger level and CHD. So it does appear that angry people do end up with heart issues later. And then remember, the last thing you need to do anytime you reject, you need to come up with some chi-squared comps that are most likely to differ. So that means, you guys, when you look at the chi-squared comps, and again, the calculator asked you where do you want me to store the comps to also. When you go into that matrix and you look at those numbers, there should be a couple that stand out to you that are pretty different from the rest. If we were not rejecting the null and if we were failing to reject, that would mean when you look up that matrix, all of those numbers would be relatively similar and small. But since in this case we are rejecting, you should be able to find in the matrix a couple values that differ quite greatly from the rest. And that's kind of insurance for you to make sure that you are coming up with the right conclusion. So it's just another like confidence booster at the end of the question. Did I do this right? Let's check those comps and see what it looks like. So here's what those two are. So here are those chi-squared comps. The categories most likely to differ were high and CHD, meaning high anger level with coronary heart disease. That chi-squared comp is 11.56. You can check that in your matrix in your calculator. And the low anger level with coronary heart disease, that chi-squared comp was 4.01. All the rest of those chi-squared comps were relatively small. These were the two that stood out. Again, that should be giving you confirmation that rejecting the null was the correct thing to do. Okay, guys, that is all for Chapter 11. Thanks for watching. Bring your questions to class. Have a good rest of your night.